Hello, everyone. Thanks for coming. Today we'll be talking about the multitask and goal condition reinforcement learning. But before that, a few reminders. Homework 2 is due today. Homework 3 is out. It will be a more lightweight homework so that you can spend a little bit more time start spending a little bit more time on the projects. But you should start with it ASAP. Especially with setting up all the dependencies and so on to make sure that everything works. And if it doesn't, please post something on ad and we'll try to help you. And secondly, there is a mid-quarter survey today. And we really appreciate your feedback. So please take the time to fill it out. We've actually incorporated a lot of the changes in the course because of that survey. Things such as switching to PyTorch from TensorFlow before, adjusting the lecture topics, the homeworks, introducing homework 0, and so on. So we really take it seriously, so please fill it out. And also thank you very much for the high resolution feedback that some of you have been submitting so far. It has been very useful to us, and we take it really seriously, so thank you. One other point is that office hours can be actually either in person or virtual. And there's been a few misunderstandings where somebody thought that it was in person and it wasn't. So please check the calendar. The calendar should be able to tell you whether it's in person or virtual and follow that. All right, so the plan for today's lecture is first we'll do a little bit of a recap from last week. And we'll finish the Q-learning aspect of reinforcement learning, which we didn't get to talk about. And then we'll dive into the multitask aspect of things. So we'll talk about multitask imitation learning and multitask policy gradients, multitask Q learning and data sharing, and then finally about goal condition reinforcement learning, which is also the topic of your homework. All right, so let's start with a short recap. So last week we talked about the anatomy of a reinforcement learning algorithm. And we talked about these 3 boxes. So there is the box where we generate the samples when we run the policy. There's a box where we try to estimate the return of the policy. So what's the sum of the rewards that the policy is going to get? And we have a few different options here. We talked about the Monte Carlo approach where we just sum the rewards that we achieved. We talked a little bit about fitting a Q function or the advantage function that allows us to do this a little bit better. And we haven't talked about the model-based part, which we'll talk about it next week, or on Wednesday, actually. And then there's the last box where we improve the policy, and the only part that we've talked so far about is the policy gradient approach, where we take the gradient with respect to our objective, and we do gradient ascent procedure to improve our policy. And today, we'll briefly talk about Q-learning part as well, and then next week, so we'll talk about the model-based part. And then we introduce this equation, which expresses the gradient with respect to our objective. And this is the gradient that we use in the policy gradient approach. And if we were to parse this equation, we have the part that corresponds to the green box, which tells us what's the return of the given policy. And this is just the sum of the rewards starting at the current action and the current state up until the end. These are the actions and state that we have actually experienced. Then we have this part that corresponds to the orange box, where we do multiple rollouts and we take the average. And then this whole part altogether is how we estimate the gradient with respect to our objective, and then we use that gradient in our policy gradient procedure in gradient ascent to actually improve on our policy. All right. Cool. Then we talk a little bit about multi-step prediction, about how in standard policy gradient, you would just sum the rewards from now up until the end of the trajectory. We had this example from a movie where what you could do instead is if you had an option to teleport to the state over and over again and live multiple futures, you would be able to estimate the sum of the rewards much better. So this is a different way that you can do this, which is the true expectation of the rewards given that you start the sum of the rewards given that you start in a given state and perform a certain action. And then we talked about the multi-step prediction where you, for instance, play chess. And when you play chess, you don't really have to wait until the end of the chess match to update your predictions. So you don't have to wait until you finish the game. You can actually start updating it as soon as you make a move. So if you made a move and you feel like you did something wrong, you can straight away update your prediction. And then we talked about how we can actually use this in the so-called bootstrap estimate. And the way we do this is the following. We try to fit a value function, and we do this using supervised regression. So we have our value function, which is a neural network parameterized with some parameters phi, that takes state as an input and outputs a scalar, a value. And then we need to fit it based on some kind of targets. So this is our value function. It takes states as the input, and output is just a single scalar that tells us how good is our policy, what's the sum of the rewards from now till the end. So one target we could have is the ideal target, which is the expected sum of the true expectation, the expected sum of rewards under our current policy, given that we start in a certain state. And we can approximate it by taking the current reward plus the value function of the next state. And we can approximate it even more, whereby rather than taking the true value function, which we don't have access to, we'll just take our current estimate of the value function at the next state. And this is what we refer to as the bootstrap estimate. So this is what allows us to make these predictions and update those predictions as soon as we make a step. We don't have to wait until the end of the trajectory. All right, so we talked a little bit about that. And then we introduced two algorithms. We introduced the reinforce algorithm, where we just sample a bunch of trajectories, then apply our policy gradient formula to estimate the gradient with respect to our objective, and then do gradient ascent. And then at the very end, we talked about the online Actor-Critic algorithm, where we also do a bunch of different rollouts. We save this kind of tuple, state, action, next state, and the reward. Then we update our value function according to this bootstrap estimate that we discussed. In addition, we evaluate the advantage function. And then we still compute the gradient, but now it has a slightly different form and has this advantage term here as opposed to the sum of the rewards. But once we do that, we apply the gradient ascent procedure. And we do this over and over again. All right, so this was just the prediction part, and that's when we finished last time. Are there any questions to this part? All right, if there are no more questions, then let's talk about how we can actually use these things, these Q functions, value functions, and advantage functions, to improve the policy. So not only to estimate better what's the sum of the returns, but how we can make the policy itself better. So far, the only way we're making the policy better is by doing gradient ascent. All right, so far we've been doing this policy gradient approach, and this was our way of computing that gradient. Or in the Actor-Critic way, we would just replace that with the advantage. So we could make the green box a little bit better by fitting our value function here. But now the question is, how can we improve the policy using some other procedure, not necessarily using gradient ascent? And to think about this, just remember that the advantage function is the difference between the Q function and the value function. So the advantage function tells us how good is an action compared to our standard policy pi that we would run otherwise. So to give you a little bit more of an intuition of what's going on, let's go back to our exercise that we had last time. So we have this little stick figure that is dreaming of being a drummer, right? And the way that this stick figure will be evaluated in their dream is that they will have to play in a month this little drumming test. And if they can play, they'll get the reward 1 and 0 otherwise. Right? And they have these free actions to choose from. They can either chill, they can watch other drummers perform and try to learn from that, or they can actually practice drums. And they start at some state, st, let's say st equals 0. So at t equals 0. So they start at the very beginning. And their current policy is this policy where they want to chill all the time. So the probability of taking action 1 is 1. So they always want to be doing this. And then we talked about the value function, Q function, and the advantage function in this case. So to test your understanding, let's change this policy a little bit. Let's say that it's not a stick figure that wants to chill all the time, but it's a stick figure that just wants to watch people play drums all the time. So now we'll say that the pi of A2 given S is equal 1. Right? So it just wants to watch people playing drums. So what do you think is the value function in that case? Yep.
And probably at 0.25, probably a bit bigger than 0. I don't know how you can learn drums from just watching someone.
All right, yeah, let's say something like 0.25.
Yeah.
So you would have like a fourth probability, 1/4 of a probability that you'll actually play this thing in a month by just watching people playing drums all the time. Okay, I think that's reasonable. What about the Q function of our current policy pi? So Q pi of ST, comma AT. Any ideas here? So Q function tells us what's the expected sum of rewards, given that we start in a given state. So this is the same state. We start at the beginning, given a specific action, and then we perform this one action, and then after that we continue with our policy pi. So what do you think this would be? Yep? Right, but this won't be just a single, so this will be a scalar for a particular action, right? So you're saying that the Q of ST, where t equals 0, of comma A1, A2. Okay, so if AT is equal A2, it would be equal to what, sorry? Right, yeah, so it will be higher than what A1 would be, but lower than what A3 would be. But it should be exactly the same as the value function, because the value function was thinking that your policy is always acting as if the A2 is the action that you're performing, right? So the Q function for ST and A2 should be equal exactly to the value function. So we established that there is 1/4 of a chance that you will play this thing at the end of the month, so let's say 0.25. Does that make sense? Right, too? Okay. And what would it be for A1 then? Yes?
Slightly less than 0.25.
That's right. It will be slightly less than 0.25. That's right. Because you perform this one action where you just chill for this particular moment, but then after this you'll continue watching people play drums. And for A3 it will be a little bit higher. All right, great. So now what about the advantage function? And let's just consider the advantage function only for A3. All right, so the advantage function would be of ST comma A3. Yes?
Small positive number.
Small positive number. Yep, that's right. That's right. So the advantage function is the difference between the Q function and the value function. So it kind of tells us how much better is this action compared to the action that I would usually take. Okay? Cool. All right, so given that we have all of these things, we have the value function, let's assume that we know it. We know the value function, the Q function, and the advantage function, and we have our current policy. And let's say that our current policy, we go back to chilling all the time, so it's this. So given all of these quantities, how can we improve the policy? Do you have any ideas of a simple algorithm that would allow us to improve the policy? Yes?
We will have a positive advantage function for the values A2 and A3. So we can leverage that so then adjust our current policy.
That's right. Yeah, so just to repeat the answer, we'll have the positive advantage for A2 and A3, so we could choose among these two, and that would, if we do that, then we'll have a policy that is better than the policy we had before. Yeah, that's great. Cool. So in particular, what we're trying to do is we have this advantage function that tells us how much better is AT than the average action according to our policy. And one particular way we can do this, we can take the argmax of that, right? So we don't necessarily have to choose between A2 and 3. We can just evaluate all of the actions and take the argmax. And that action will definitely be better, or the policy that performs that action will be no worse than the policy that we currently perform. And so it will be at least as good as any action from the policy, regardless of what the policy actually is, right? So we don't need to have access to the policy. We just need to have access to the advantage function. So let's say our policy would look exactly like this. So with probability 1, we'll be choosing the argmax of the advantage function, and this will be our action. 1 second. And with probability 0, we'll be doing anything else. Yes?
I just had a quick question about the value function. It's not super hard. How does It seems like the hardest part is actually getting a good value function because, I don't know, is it common in practice that it actually fits very accurately?
Yeah, that's a great question. So the question is, it seems that just fitting the value function is the problem, and whether it happens in practice that we can fit it very well. Yeah, so I think in practice, we usually don't fit it extremely well. We also use algorithms that we will learn about in, I think, 2 minutes or so, where we are constantly changing the underlying policy, and the value function is kind of constantly changing because it's evaluating value of different policies all the time. And we don't fit it perfectly, but we fit it well enough to actually get better and better policies. But you're right, fitting the value function is actually difficult. Yeah. Cool. All right, so we have this new policy that we know that should be better than our current one. And this is what leads us to an algorithm called policy iteration. So it's a very simple algorithm where in the first step, we'll be evaluating our current advantage function, right? So the advantage function of the current policy. And once we have that advantage function, we'll set the policy to this new policy, and we'll do this over and over again. And the new policy will be equal just the argmax of the current advantage function. Right? So very simple algorithm, and we're iterating over the policy. So that's why it's called policy iteration. Okay, cool. And as before, the advantage function is equal to the Q function, which is the reward plus the value function at the next step, minus the value function of the current step. All right, so now there's 2 steps that are sort of magical that get us to the final algorithm that is actually extremely useful. Yes, there's a question.
Why even bother defining something like the advantage if it's just defining in terms of the Q and the V? Like is it called stability or something like that?
Right, so the question is why even bother defining advantage function if it's defined in terms of Q and V? Why can't you just use Q instead? Yeah, that's so the reason why people usually use advantage function is because it's better normalized, right? So you subtract kind of the thing that is your baseline, which is the value function. However, we'll just learn about it in a second. People also use Q functions instead. Yeah, you can use that. Yep.
Another part is it gives us lower variance.
That's right.
Yeah.
So because it's normalized, it gives us lower variance, and because of that, we can do policy gradients a little better. All right, so now let's discuss 2 steps that are kind of interesting that would allow us to get finally to Q-learning algorithm, which is applied all over the place. All right, so we had this policy, which was taking the argmax of the advantage function. And when we were doing this argmax, what we're actually doing, if you remember the drummer example, we do this argmax just to give us the index of the action we should be picking, right? So we take the argmax over the advantage, and that just tells us pick A3, right? It just gives us the index. Then we know that the advantage function is equal to Q, which is expressed like this, minus the value function. And we know that the argmax of the advantage function would be exactly the same as the argmax of the Q function, right? So we can remove the value function because it's not dependent on the action, and the argmax will be exactly the same. So let's do that. It will be a little bit simpler. We got rid of one term, so now we can just say that the Q function is equal to the reward plus the value function at the next step. Cool. So now we can change the argmax here to be the argmax over the Q function, and in the policy iteration algorithm, rather than having the advantage, we'll have the Q function over here. Right? So we kept everything the same, we just changed advantages to Q. So now here's one trick that we'll start with. So because we are using this argmax just to give us the index, and then as soon as we have that index, we'll have to evaluate it in the next step again. Right? So we kind of have this new policy, but this policy is only useful as far as evaluating the Q function of that new policy. We don't actually use the policy itself. We just use the value of that policy in the next step. So the idea is, let's skip the policy entirely. Let's kind of get rid of the middleman and just compute the values directly. So the argmax of our Q was the policy, and the value of that new policy would be actually the max of the Q. Right? So the argmax was kind of giving us the index of the action, but the max of the Q is giving us the value of that new policy, which was the argmax. Right? This is a little bit of a trick, but it's actually extremely useful. All right, so this approximates the new value. All right, and that leads us to a value iteration algorithm, which is kind of the similar version to policy iteration, but now we'll be iterating on the value itself. So this is how it works. We set the Q to be equal to the reward plus the value of the next step. So this is what the Q function is. But then we'll update the value function to be the max of the Q. Right? So this is kind of like in the previous step. Here we were updating the policy. Here we are updating the value of the new policy. So because the new policy will be the argmax of the Q, we can just say that the value of that new policy, that is the argmax of the Q, is just the max of the Q. And we do this over and over again, and we are iterating on the value, and this is value iteration. Cool. So that means that in the green box, we have this Q now. And to improve the policy, we are just setting the value is equal to the max of our actions of the Q. Cool. So now the question is, we have this algorithm, right? And now we have to implement it, right? Like we have to have some neural networks that actually learn something and try to fit either the value function or the Q function. So this is called value iteration. So let's maybe start with value function, all right? We'll try to have a neural net that represents a value function. So it takes a state as input and outputs a scalar, which is the expected sum of rewards. And let's see if we can do that, all right? So let's write it on the board here. So let's see, our value function, v of s, parameterized with some parameters phi, would be equal to the max over actions of the Q, but we don't have a neural network that represents the Q. So let's express Q in terms of the V. And we have that in the line, in step number 1. So this would be the max of R of S comma A plus the discounted expectation of the value at the next state. All right, and this expectation is with respect to P of S prime given S comma A. All right, so this would be our target for the value function, right? And we'll be trying to minimize the difference between the two, and we'll optimize the neural network to do that. There's a question. Yep?
Since you're taking expectation, don't you still need to know like the transition like dynamics, like the transition probability?
That's a great point. So the question was, don't you need to know the transition dynamics because you're taking the expectation and you need to know what the next state is? Yes, that's true. So there's this problem with this equation, which is if we were actually try to implement this, we have the value function that takes a state as input. So we have state that is available to us. And then we have to take the max over all the actions that are possible, right? So we can try different actions. So we would need to know the reward function. Let's say that we know that for a specific state, we know, given a specific action, what the reward function is. But then we would need to know what would be the next state that I would end up in, given that action, so that we can compute the value function of that next state, right? But to know this, we will be testing different actions, right? Because we'll need to take the max over actions. So to know this, we would need to know what would be the different states that we would end up in given those different actions, right? We would have to, let's say we have 10 different actions to choose from. For each one of these actions, you would need to know what the next state is so that you can input this to your value function, to your neural net. So you need to know the transition dynamics, which was the question. Yep.
Assume that those are just like Monte Carlo samples and say, okay, I've observed one transition and I've taken that action.
So the question is, can you just randomly sample?
Because you have an expected value, so like a sample. If you have that process, because your data that you're going to obtain is from that distribution, should the samples from that distribution converge to the expected value?
Right, but to sample from this distribution, you don't actually have access to all the different actions that you could perform. You only have access to the actions that you did perform.
Yeah, right, okay.
So in that case, you would need to kind of know, had I performed that other action that I've never actually tried, what state would I end up in? And you don't have access to that. You don't know what the future would be. All right, so the value function doesn't quite work. Right, and that's what leads us to the final algorithm, Q-learning. So again, we have the value iteration algorithm, but now instead of fitting the value function, let's just fit the Q function instead. Right? So we keep everything exactly the same, but now instead of learning the value function, we'll be learning the Q function. So let's do that. 1 second. Okay, cool. So now our targets will be trying to fit a Q function, parameterized with some parameters, s comma a, and this would be equal to the reward of s comma a plus the expected next value, and the next value is the max of the Q. Right? So the max over actions. This is a different action. This is not this action. That is the input. This is, let's call it A prime, of the Q at S prime, comma A prime. Right, and this is the Q function that is parameterized with the same parameters. Right, so it's the exact same thing. Now we're fitting the Q function instead of the value function. Yes?
Like how are you getting the S prime in that approximation?
How are we getting the S prime? Yeah, that's a great question. So let's think about this equation first, and then we'll get how we get the S prime. So now the input to our Q function is state and action. All right, so our Q function looks a little bit different. All right, our Q function is now has two inputs, states and the action, and then outputs the value. Right, so this is expressed here. And given state and an action, we have access to a reward function, so we can compute the reward. And now we have this max term again, but now it's a little bit different. So the max is taking the max over all the actions of the Q function of the next state. Right? But now let's ignore the next state for a second. But in terms of the actions, we can actually do this, right? Our Q function is dependent on both state and action. So we can plug in all kinds of different actions that we haven't taken and compute the max. Right? We don't have to simulate now what's going to happen next. We can just plug in the actions because this is part of the input of our function and just try it out and see what happens. Now, how do we get the next state? So the way we would do this is actually similar to how we did what we did in the Actor-Critic case. We would just be saving, so this next state here, this is just the function of the current state and the action. Right? It's independent of the policy or of the Q function or anything like this. So what we'll be saving as we run the policy in the world, we'll be saving so-called SARS tuples. So we'll be saving state, action, reward that we got, and the next state that we observe. And then from that, we'll be approximating these expectations from the states that we have actually seen. So we can just record, as we run the policy, we'll be recording these 4 values so that we have access to S prime that we've actually experienced. And here, we will be plugging that S prime that we've seen. Yep.
Like in the data, you just have like multiple different S primes, right? Because it's like not deterministic which next state you think. So like, how do you pick one like just based on frequency?
Right. So you might experience multiple S primes. Yeah. So we'll iterate through all of them. Right. So like for every source tuple, you'll perform this, and then this is how you would approximate this expectation there. Right. Cool. So this is what gets us to Q learning. Doesn't require simulation of actions. And we can do this. All right, so a quick recap, a few definitions that we introduced here. We have the value function that tells us the total reward starting from state and then following our policy. So in other words, it answers the question, how good is the state? Then we have the Q function, which is the total reward starting from S, taking a single action, and then following the policy, which answers the question, how good is the given state action pair? And then for this optimal policy, we just introduced this equation right here. We have this dependency that says the Q function, the optimal Q function, which will be depicted with star. So this is now the optimal policy is pi star is equal to this expectation. And this is the reward that we got for the given state and action. So this expectation is actually unnecessary for the reward, plus the max over actions of the queue of the next action. And this is what we refer to as the Bellman equation, or the Bellman optimality equation. And this is one of the most important equations in reinforcement learning. All right, so let's go back to our drumming example. So we talked about the value function, the Q function. What is the Q function of the optimal policy? So our Q star. So this is not Q pi, which is the current policy, and the current policy is, the stick figure wants to chill all the time. What's the Q function of the optimal policy, pi star? So what's Q star? Any ideas? Yes?
For A3, it'd be 1, because you're starting in state 0, and if you take A3, you're going to then perform A3 afterwards, because A3 you're always doing that as optimal policy. So in that case, you just converge to the best one. In A2, I would say it's like a bit less than 1, because you're going to perform A2 once and then do A3 all the time, and the same as for A1, so you'll have like one day off and then keep practicing.
That's right, yeah. So just to repeat this for everyone, for A3, it would be 1. That means that you're practicing all the time, including the current time step. For A2, it would be a little bit less than 1. You just watch for a second and then you practice all the time. And for A1, it will be a little bit less. So you take an hour off, let's say, you chill, and then you practice for the rest of the month. Cool. And what would be the value function, the V star of S0? Please just don't be shy, raise your hand. Any ideas, or just shout out the answer. Yes? That's right, it would be 1 because the optimal action would be A3. Yeah, so this this assumes that you're acting optimally straight away. Cool. All right, so we introduced this fitted Q iteration algorithm, which works like this. We have a few hyperparameters. So first we collect the data set using some policy, and we collect these source tuples, so state, action, next state, and the reward. And let's say we have a data size n, data set size n, and some collection policy that we collect the data with. Then we set our targets for the Q function according to the Bellman equation that we just introduced. And then we minimize the distance between the Q function and the targets. Right? And our Q function is this neural net that takes states and action as an input and outputs a single scalar value. So we do this over S gradient steps, right? We can do this a few times. And then we do this, we can iterate in terms of updating the targets k times, right? So we can apply a few gradient steps, and then we would update the targets because now our Q function has changed, so this max term will be changing. And it's an iterative procedure, so we're approximating Q star better and better over time. And then we go back to collecting the data set. And as the results, we can get the policy by just taking the argmax of the Q. There's a question.
Yep. In step 2, do we have to do like a bunch of forward passes, one for every possible A prime?
Yeah, that's a great question. So the question is, do we have to do in step 2 a bunch of forward passes, one pass per A prime? Technically, yes, but you can batch them together. Yep.
In terms of step 2, I think you should write phi prime instead of phi, because in step 3 you're gonna take argmin with respect to phi, and the yi is the target, and if they share the same parameters, we're gonna, technically we're gonna detach the gradient from target's rank.
So you're saying that this Q over here should have a different parameters than the Q over here.
Yeah, because like a target network.
Right, yeah. So this is one of the implementation things that people introduce to make this procedure much more stable. And they introduce a target network here because this network is constantly changing. We're constantly applying gradient steps to it, and it causes some instability in learning. So instead what people do is they copy the values of this network once, and then use that target network with copied values here, and then apply the the gradient steps to this network that is constantly being updated, and every now and then they would update the target network to the network that they've been using. Yeah, that's an implementation trick that people use. That's right. All right, so a few important notes. We can reuse data from previous policies, right? So here we are just using some policy. It's not an on-policy algorithm. We don't have to be rolling out from the current policy. This is any policy. There's a question.
Just one quick question going with the A. Like, if it's still fine, like doing a batch forward pass if it's discrete, and what would we do in the continuous case?
Yeah, that's a great question, and we'll answer this in 1 minute.
Oh, okay.
Yeah, great question though. The question was, how would you do it in the how would you take that max in a continuous case, and can you batch the actions then? All right, so we can reuse data from previous policies. It's an off-policy algorithm. We don't have to be running the policy that we are currently learning. We could be running any policy. In practice, what people do is they push these source tuples to replay buffers, and then they have one big replay buffer with all the data, and they just sample from that buffer to do the updates. And importantly, this is not a gradient descent algorithm, right? So even though we are trying to fit the Q function to the targets, and this is where we apply gradient descent, the algorithm, how we learn better and better policies, is a recursive iterative algorithm which uses dynamic programming. All right, so here we are constantly updating our Q function according to this formula, and this doesn't require gradient descent. We use gradient descent to just fit the Q function to the current target. All right, so now a quick example. And this is the example of continuous actions. So we'll try to apply Q-learning to robotics. So this is our algorithm. So now the question is, how do we take that max over actions where robots move in continuous space, right? Like their actions are continuous. They need to get to a certain pose, for instance. So we can just enumerate all the actions. This is a continuous action. So one way we can take that max here is by running a simple optimization algorithm. And there is this gradient-free optimization algorithm called cross-entropy method, or CEM. And the way it works is actually really simple. You would start with a normal distribution, all right? And then you would sample a bunch of actions from that normal distribution, and then score each one of them, right? So I would start with, let's say, 20 actions. I sample all of them, and then I query my Q function, what's the value of each one of those actions, right? And some of them will have higher values, some of them will have lower values, so the higher values here are in gray. And then I can do another iteration of CEM, where I would now fit a Gaussian to my elites, to the best actions the actions that achieve the highest score, and then perform this procedure again. Yep.
Like evolutionary method? Yeah, so
this is a type of evolutionary algorithm or gradient-free optimization method. You can use any other optimization method to just find the max of a function. This is just a very simple thing that was actually applied to robots. Cool. All right. So let's do all of this. So this is the work called QT-opt done by Dmitry Kalashnikov et al. At Google Brain. And the way it works is the following. We store data from all the past experiments. Then we have a bunch of buffers, the off-policy buffer, where we put all the data in, as well as the on-policy buffer, where we currently collect the experience. We have our Q network, which is parameterized by some parameters theta. And then we have this separate process. This is running at large scale. This is our parallel. So we have the separate process that's called the Bellman updater, which is just computing the target values for the current Q function. All right? So all it does, it just computes the reward plus the max of the next Q. And this uses the CEM optimization to get that max. And then once it does that, it would push these targets to a buffer as well. And then from this buffer, we'll have a set of training jobs that are just doing gradient descent, that are just trying to fit the Q function to that Q target and update the parameters of the neural net. This is heavily parameterized and running on thousands of machines. Cool. So this was applied to grasping, and the MDP definition for grasping was the following. So the state was the image captured by the camera that was here over the shoulder camera, and this is what the image looked like. The action was 4 degrees of freedom post change in the Cartesian space. So it was controlling, it was a top-down grasp. It was controlling the position as well as the yaw, the orientation here, plus the gripper control. So it could also tell whether the gripper should close or open. And the reward was binary. So it would just say at the very end of the trajectory, if you grasp something successfully, you get reward 1, 0 otherwise. That's it. And we actually implemented an automatic success detection mechanism for this, which was very simple. So at the end of the trajectory, the robot is either holding something in its hand or it's not. So what we would do is we would take an image when it's holding, or at the end of the episode, and then we would open the gripper and take another image. Now, if you were holding something, then the difference between these two images would be non-zero, right? Because you just dropped something into the bin. If you didn't hold anything, the difference would be 0. So a very simple automatic success detection mechanism. All right, so in terms of the results, we used 7 robots to collect over 580,000 grasps. And it was evaluated on previously unseen objects. So we'll just like drop a whole bunch of different objects into the bins, let the robots run with them and practice grasping. And then we would evaluate it on objects that the robots never seen before. And the success rate was really high. It was 96% success rate. And that was actually really surprising to us that we could get to a number this high, because grasping is not a new problem. People have been working on grasping for 50 years or so. And this is, I think, the first time where we were able to see that this problem can be actually solved and we can grasp objects that the robot's never seen before. And here are some examples of strategies that the robots learned. So here you can see that this grasping is kind of full of contact and it's interacting with the environment, which is very difficult to prescribe or to engineer up front. So here, it's trying to singulate the object, it's moving the other objects apart and so on to grasp it. Here there is an example of a reactive behavior where it's trying to grasp this tennis ball. And I think in a second you will see an example where there's a mean experimenter and it's moving the tennis ball away. And the robot understands that the ball is not there anymore and it follows it and gets to a state that has high Q value. Or here's one more case where it's a very flat object that is really difficult to grasp. And the robot learned how to retry and kind of fully understand what it means to grasp something. And it tries it a few times until it gets it right. So it kind of understands that some actions or some Q values for some of those states are not as high as they should be. So it runs this max to find the better action until the moment where it actually grasps it and then succeeds. All right, so to summarize Q-learning, in terms of pros, we have, this is more sample efficient than on-policy methods. We can incorporate off-policy data, including a fully offline setting that we'll discuss in I think, 2 weeks. And we can update the policy even without seeing the reward, kind of like in the chess match that we discussed before. As soon as you make the next prediction, you can update the policy. And it's relatively easy to parallelize, how we just saw in Qt up case. And in terms of the cons, there's lots of tricks to make it work, including target networks and other things. And potentially it could be harder to learn than just the policy itself, because you need to model kind of the landscape of all of the actions. All right, any questions? Yes?
If you go back one slide, how did you guys encode the fact that they were supposed to pick up the tennis ball, for example?
Right.
Part of the state space?
Yeah, great question. So the question was, how do you encode the fact that you wanted to grasp a tennis ball? This was just an accident. So we didn't encode it in any way. So this is not an instance grasping system. It just grasps anything that it sees. Yep.
So for it's taking them apart, it just grabbed any of them. It wasn't like,
right. So if you let it run for a little longer, it would eventually pick all of them one by one. Yep. One question.
So in the Qt up example you just mentioned, you used the CM method to handle the continuous action space. So I'm curious to know why you didn't use like DDPG to handle the continuous action space, because for me it's quite intuitive to use DDPG than CM. I'm curious to know, are there any comparisons between these two methods?
Right, yeah. So the question was, why didn't we use some other method like DDPG that is fairly popular, that is another way of getting the max of the Q function in a continuous case? The main reason is because it was much simpler to do it this way. And we didn't want to have a separate actor, and there's actually a lot of instabilities that come with using an actor-critic method like this. So we just wanted to make it simple, easy to parallelize, and it was good enough. All right, cool. All right, so that's the end of the recap and Q-learning. Let's dive into the multitask stuff, the exciting part about imitation and policy gradients. So we talked a little bit about imitation learning before. We had this example where we had human drivers collect some images and the actions that they were performing, and we would put them in a big training data set and then do supervised learning on it, doing imitation learning. So now the question is, how do we do this with multiple tasks, right? So first question is, well, how do we optimize multitask imitation learning setting? And the answer is really simple. And this is the reminder from lecture 2 that Chelsea gave. We just use the vanilla multitask objective where we minimize the loss across different tasks, right? So we can have some kind of way of specifying which task it is, and then we can compute the loss for each one of the tasks and take the sum of those and minimize that. So it's exactly the same as supervised learning. So we can use same architectures, stratified sampling, everything that you learn about soft or hard weight sharing, and so on. Very simple. Right, so the other question is, how do you specify a task? Right? So let's say you're trying to teach a robot something, you need to specify multiple tasks. Using imitation learning, you collect demonstrations for each one of them. How would you specify the task? Any ideas? How would you communicate to a robot what task you wanted to do? Yes?
I think a single entity can be considered as a task, and different has to respond to different entities with different points and like transition that.
That's right, but you have to specify the task to a robot somehow. So what would you use for that? How would you describe the task? Yes?
Specifying the reward function.
By classifying a reward function? Is that
Specifying the reward function.
Right, so different tasks would have different reward functions, but still you would have a neural network that would need to be conditioned on a task, right? And this conditioning needs to be specified somehow, right? Like you need to tell the robot or you need to explain what kind of task you want it to do. It would have different rewards for all of these tasks, but how would the robot know which task to perform? Yes? Yeah, you can use a one-hot vector, right? So it would be just one hot telling you which task you're in. Yes?
You can use demos, code images, language.
Yeah, right, yeah. You can use demos, so you would perform a demonstration and that would be some kind of embedding of this demonstration would be the description of a task. You can specify it by natural language. You can specify it by a video, by a goal image, all kinds of different things. And these different things have different trade-offs. So there's this one work that was published at Karol by Eric Jeng et al. Called BCZ. And the way it works is the following. So they collected a big data set of demonstrations, which resulted in this diverse multitask data set. So they were doing many different tasks. And then they were actually conditioning the policy on two different things. On the video, it's a human video of performing a task, and a natural language description as well. And then they would, based on this, they would test how well does it generalize to a task that it's never seen before. Right? So they would generalize on tasks that haven't been seen, which is kind of a novel thing to do. Their architecture looks like this. This is the state, so they take the image from the camera, then they random crop it, downsample it, so they have this smaller image, which goes through a pre-trained ResNet network and then does a few operations and eventually outputs the action that the robot should do. And then they have this way of encoding the task, and they have two different ways here. So they can either take the human video, so they record human videos that are paired to the task that the robot was trying to do. They pass it through a video encoder, and this ends up being in some kind of embedding vector in some latent space. And they also have a natural language description of the task, which goes through a language encoder. In this case, I believe this was a pre-trained language model, which ends up in some space in this embedding space, and then they use film conditioning to condition this ResNet on the task that they want to do. In terms of the loss they use, so they take they do the minimum negative log likelihood, so they're minimizing this over all the tasks as we just discussed, and they have the behavioral cloning loss, where ZI here depicts the embedding of the task you're in. And then in addition to this, for this to work well, they added one more loss, which is the language regression loss. So they're trying to minimize the distance between the video encoder and the language encoder for a specific task. And this makes the video encoder a little bit better. All right. So in terms of the results, here are some of the tasks, the held out tasks that I've been evaluating it on. And you can see that some of them kind of worked, some of them work fairly well, like 82% or so. Some of them don't work at all, like some of the language descriptions that you see here, like place banana in a ceramic cup. And overall, the held out task success is just 32%. But keep in mind that this is the first time where we're actually trying to evaluate something on tasks that you've never seen before. So they trained on a completely different set of tasks. So here we are testing generalization to new tasks. So there is non-zero success for 20 of the 28 tasks, and the average success of these held out tasks was 32%. And here are some examples of what this actually does. So here is a task that it's never seen before. For instance, push purple ball across the table, and you can see that it does that. Or here another task that it's never been seen before, place bottle in a tray. Right? So in this case, they use natural language as the task specification, and this allows them to do some zero-shot generalization where they can specify a different text command, and the robot does that. All right, cool. So now we also talk about reinforcement learning, and we talk a little bit about what is a task in reinforcement learning, and we talked about this definition, the MDP, where we have the state space, the action space, the initial state distribution, the dynamics, and the reward. So an alternative view that was already said in the class was to add the task identifier as part of the state. So we can just say that our original state was this S bar, and then we'll add our task description, ZI, either natural language or something else, and this tuple would be our new state. So now our new state also encompasses what task you're trying to do. And if we take that view, then we can just say that this multitask reinforcement learning problem is just another MDP, right? So in that case, the MDP would be the state space is equal to the union of all the state spaces of all the tasks. The action space is the union of all the action spaces. The initial state distribution is the mixture, and then it has some dynamics and the reward function. So it can be cast as a standard MDP. All right, we also talked about the goal of reinforcement learning in the previous lecture. This was the single task case. The multitask case is very similar. So it's the same as before, except now we have this task identifier that tells us which task we're in. An example of this would be one hot task ID, or a language description, or a desired goal image. Now, if we use the goal state, if we use the desired goal state, then our ZI, our description of a task, would be equal to some state SG, right? So it will be in the same dimensionality, in the same space as the states themselves. And this is actually a really important case that we'll spend a little bit more time on. And this is what we'll be referring to as goal condition reinforcement learning, right? So we're conditioning on the goal that we actually want to see in the world, that we want to achieve. So what is the reward in this case? It could be the same as before, or for goal condition RL, the reward could be just the distance or the negative distance between our current state and the state that we want to get to, right? So it will be just the negative distance between the two. Some examples of that would be the Euclidean distance or a sparse reward. So if the two states are exactly the same, you get a reward, otherwise you don't, or something else. So this is the goal condition RL case, the multitask RL case, fairly simple. All right. Yeah, so in terms of the conditioning, we already discussed two different ways of specifying the task to an agent. And it turns out that it actually matters how you specify it. And it's not just that it matters because it's maybe more convenient to talk to a robot than specifying a one-hot vector to a robot, but it actually also helps with learning. So to discuss this, we'll look at this benchmark called MetaWorld, which consists of 50 different tasks, 50 different manipulation tasks that have the same robot, the same state space and action space, but they do slightly different things, right? Simple manipulation tasks that you see here. And it turns out that when we evaluate whole bunch of different multitask versions of popular multitask reinforcement learning algorithms. They don't work that well. So even though you can solve each one of those tasks separately quite well, if you put them all together and you try to learn them all together, it doesn't work that well. So the success rate is at like 50% or so. So there's this idea introduced by Sudhani et al. Called CARE, where instead of specifying tasks as one-hot vectors, which is what was done here before, they would introduce so-called metadata right here. So the metadata would be a short language description telling you what the task actually is. So for instance, it would say, insert the peg inside the hole or something like this. Now they would use that metadata, they would pass it through a pre-trained language model and then have another feed-forward neural net to get some kind of context, right? And they would take this context vector, and then separately they would have the state that has to pass through k different encoders that are being trained. And then they would look at the output of all of these encoders and then do attention over those according to the context that they got from the metadata, from the pre-trained language model. So kind of the language model tells you what part of the context or which encoders you should be paying attention to. Then they pass it through an MLP, so a feed-forward neural net, and then they combine these two, and then this is the representation of the task, and then they run it through the policy algorithm. So it's kind of, it's a different way of conditioning, right? So they're still running the same multitask reinforcement learning, but now the task is specified by the metadata, and there is some kind of trickery as to how this is being processed, but the important part is that there is some language description that tells you the connection between different tasks. And it turns out that it works a little bit better. And they actually showed a few different ablations in their paper showing how this works and why that is. But one particular one that I found interesting is right here. So they tested on 10 tasks, and these are the descriptions of the tasks. And here they show this confusion matrix showing you the similarities between the different tasks. So in here, this matrix right here, B, this is the cosine similarity between the pre-trained language embeddings of those tasks. So we can see that tasks number 9 and 10 seem to be very similar, and this has something to do with pushing a window. So the pre-trained language model puts them kind of close together. C is the case with their 6 encoders, so with their CARE model. And they can see that there is actually a lot of similarities between the different groups of tasks. So not only 9 and 10 are similar, but it looks like 4, 5, and 6 are fairly similar, right? So 4, 5, and 6 is open a door with a revolving joint, open a drawer, push and close a drawer. So it seems like the motions that you have to perform these tasks, and also the way that they're described, share a lot of similarities, so they can be mapped kind of together, and metadata helps with that. And then they also show what this matrix looks like if they don't use metadata at all. So there is no similarities between the tasks. So it seems that the right context not only can help us interact with the robot, but it can actually provide interesting context for the training algorithm itself, right? It shows certain similarities between the tasks. We describe tasks in a certain way because there are similarities how we perceive the world, right? Like if you push something or pick something or pull something, the reason why these words are sort of seem similar is because these correspond to similar activities, and the model can actually take advantage of that. All right, I'm gonna skip some of this because we're running out of time. But I also wanted to tell you a little bit about the difficulties of multitask reinforcement learning. So when we look at MetaWorld for the first time, we saw that if we train all the tasks independently, so each task by itself, for one of those 50 tasks, it actually works much better than if we train them all together using one-hot conditioning, or even using any other conditioning. So we tried different hypotheses. We tried to making the network much bigger, collecting much more data, trying all kinds of different things, but none of them really seemed to help. So then we looked at one more thing. We looked at the gradient cosine similarities between different tasks. So in particular, we took the task 0 and task 1 and just plot over the number of gradient steps what's the gradient cosine similarity. So the gradients for different tasks, how do they relate to each other? And it turned out that it's all over the place. So sometimes it's positive, so that means that they're aligned. sometimes they're perpendicular, which means the cosine is 0, and sometimes they're negative. So one task is pulling in one direction, the other task is pulling in another direction, which kind of seems to be a problem. So then we came up with this very simple algorithm, which says if two gradients conflict, then let's project each onto the normal plane of the other, and if they don't conflict, we don't do anything. So it's a very simple algorithm that looks at the gradient vectors for two different tasks, and if they're conflicting, so if this angle here is more than 90 degrees, it would project one of the gradients onto the normal plane of the other, and the same with the other one. And if they're non-conflicting, we won't do anything. All right? So we apply this. So first thing we started seeing is that we call this algorithm a PC-grad, and this was this is the work led by Kevin Yu. And the first thing we start to see is obviously because of the definition of this algorithm, we don't have conflicting gradients anymore, right? Like every time the gradient is conflicting, we'll project it, and it's not conflicting anymore. So now the plot looks like the one in green. But then in addition, what we started seeing is that the performance now with the PC-grad in purple is actually much, much better than what we've seen before. So not only it's better than the things that we've seen before when we train them jointly, but it's also better than if we train the tasks independently, right? And that seems to indicate that there is actually quite a lot of structure that you can take advantage of in the meta world tasks, which is not that surprising. These are similar manipulation tasks, and by fiddling a little bit with the optimization, you might be able to extract those advantages and actually see that. And here, I think we're just scratching the surface of the problems that you see when optimizing for multiple tasks and so on. And it shows that even very simple algorithms can actually improve the performance quite significantly. All right, so to summarize, the multitask RL algorithm, we change a policy to now include also the task information, CI. We can do the same with the Q function. The Q function can now also incorporate the task information, ZI. And it's analogous to multitask supervised learning, so we can use the same things again, stratified sampling, soft, hard, weight sharing, etc. And if it's still a Markov decision process, well, why can't we just apply standard RL algorithms? And so far we've talked about more or less standard RL algorithms, maybe with the exception of PC-grad. And the answer is, yeah, you can do that. And it actually works fairly well. But we can often do much better than this, and that's what we'll discuss next. And to think about this, what do you think we could do? What is different about reinforcement learning in contrast to supervised learning? What are the other aspects that we can control that could help us here? Any ideas? Yes? We can choose where we want to explore. That's right. Yeah, exactly. So the data distribution is controlled by the agent itself. So the question that we'll try to answer next is, can we share the data in addition to sharing the weights? And how should we share the data, or how should we explore so that we can take more advantage of the multitask RL algorithms? All right. So this is where we talk about multitask Q learning. Are there any questions at this point? All right, cool. So to explain this data sharing problem, let's consider the following example. Let's say we are playing hockey and we want to learn two different tasks. One task is passing, and task number 2 is shooting goals, or scoring goals, I guess. And let's say you collected some experience where you were trying to make a good pass, but you were trying to shoot at a goal, but accidentally you performed a good pass, right? So it's not what you intended, but it just happened this way. So what can you do in this case in the reinforcement learning setup? Well, you can store the experience as normal. So you can store that experience of you performing a pass, but you're trying to shoot a goal as just an example of trying to shoot a goal, right? The example of task 2. But in addition to this, you can also relabel that experience with task 2 ID, right? So just you can pretend that you're trying to shoot a goal from the very beginning. I messed it up a little bit. So relabel the experience with task 1 ID and the reward, and store that as well, right? So you're trying to shoot a goal and you ended up passing, so you can store this as an example of shooting a goal, but you can also store it as an example of passing. So you can kind of double the size of the data set now. And this is what we're referring to as hindsight relabeling or hindsight experience replay, or in short, HARE. Cool. So the way the algorithm would work with this, and this is actually quite important, and this will be, partly this is also the topic of homework 3. It would work as following. We would collect the data using some kind of policy, as we do in reinforcement learning, and this would result in some state sequence, some action sequence, and some description of a task. So we're trying to perform task I. And we have the reward associated with that task. Then we'll store that data in a replay buffer, as we usually do. And then we would, in addition, perform this hindsight relabeling procedure. So we'll relabel the experience that we just collected, but we'll relabel it for a different task, for a task TJ. Right? So it's the J task, not the I task that we originally collected the data for. So now that data would look like this. It would still be the same sequence of actions, same sequence of states, but now rather than saying that this was ZI, we'll just say this was ZJ, right? Like I was actually trying to pass. And then we would also have to relabel the reward as the reward that is the reward for task J. Right? So we have to now score it according to did you pass or did you not pass. And then we can store the relabeled data in the replay buffer as well. And then update the policy and do this over and over again. There's a question. Yeah?
Do we only do this hindsight relabeling if our action is actually useful or like meets a certain threshold for this other task, or do we always do it?
Yeah, that's a great question. So the question is, when do we do this? When do we do this relabeling? Do we do it only when we perform something useful for this other task or not? Yeah, and this is actually one of the big questions in reinforcement learning as to how to do it. So let's consider a few options. Which task should you choose? So one idea would be to choose it randomly, right? Just like relabel it to any other task. But the idea that you had was, well, maybe we should relabel it to task or tasks in which trajectory gets high reward, right? So only if you actually pass to someone, you should relabel it as passing. If it resulted in something completely random, then you shouldn't relabel this as passing. And there are different options here, and these different options actually have really big influence on the final results. There's other options here as well. And here are some papers that talk about different ways how you can relabel that. And these either use certain heuristics or look at offline cases or offline reinforcement learning cases and so on. But usually I think they correspond to something that you described, which is relabel to tasks that have a high chance of achieving a reward, or to tasks that seem like something that you could have done had you tried that task. Yes, there's a question?
In this case, do all tasks have same dynamics?
Yes, so we assume that they have the same dynamics. That's a great point. So when can we apply relabeling? So reward function needs to be known because we need to evaluate now the state for a different task. Dynamics need to be consistent, as you said, across goals and tasks. And then we also need to be using an off-policy algorithm. There is actually a way to use on-policy algorithms with that as well, but off-policy algorithms works much better. All right, so one more example as to why off or on policy, how do they compare here? So let's look at another example. So let's say one task is to close a drawer, and the other task is to open a drawer, right? These are the two tasks. So you get a high reward when the drawers are closed. In the other case, you get the highest reward when the drawer is fully open. So now the question is, can we use episodes from drawer opening tasks for drawing closing tasks? But more importantly, how does that answer change for Q-learning versus policy gradient? And for the purpose of this exercise, let's assume that if you're trying to close a drawer, you will not accidentally open it. Or if you're trying to open a drawer, you will not accidentally close it. Right? So these tests are kind of completely orthogonal. You can't succeed at a task by trying the other task. So what do you think? Can you use the episodes from one task for the other? And how does this answer change for Q-learning and policy gradient? Any ideas? Yes?
Pretty moderate, so they can have the one task and relabel it for the other task and being successful at that task.
If you failed, sorry, say that again?
Well, the tasks are binary, so if you fail at one task, you've succeeded at the other. It's either open or closed. So as long as the fact that it has the ability to relabel that, then that's not the threshold to, as a training base point.
Right. So the answer was that, well, it's a binary set of tests, so the drawer is either open or closed, so you can always relabel it as one of the other. So let's say that the drawer can be also half open, and in which case you don't get rewards for either of them. Right, so like the drawer is like this. You don't get rewards. You didn't open it. You didn't close it either. Yes?
If I understand correctly, we'll get a bunch of data of us opening the drawers.
Okay.
For the drawer closing task, the reward for all of those examples are going to be 0. That's right, for Q learning, you won't be able to use it correctly because Q learning requires you to have to like at least have seen the reward. That gets like good value.
Right, yeah, so it's partly the right answer.
Okay.
So yeah, just to repeat the answer, you're saying that when we look at the data that we collected by trying to close the drawer, the rewards for opening the drawer for that data will be 0. And then you said that because of that, Q-learning wouldn't work. Now the answer is actually, so this is the really good point, that when you try to close the drawer, that's what I was trying to get to, you won't open it, so the rewards for that will be 0. But now the answer would change for policy gradient versus Q-learning. And let's take a look again at the policy gradient estimation. And this here, the gradient is dependent on the rewards that you actually achieve. So if the rewards are 0 for when you're trying to close the drawer data set, and you relabel it to opening the drawer, so these rewards are 0, then this gradient will be 0. Right? So with policy gradients, you can't really use the negative examples of other tasks for your current task. For Q-learning, however, you can use that. So Q-learning, remember the chess example, you can actually take into account any interaction, and you can use that interaction to update your Q function. Yes?
If you see the rewards are +1 and -1, what does that make it?
If the rewards were +1 and -1, how would that change things? Yeah, so I think what would happen in practice in that case is that you would try to normalize the rewards and subtract the baseline. This is how people actually implement this in practice, so that the rewards are between 0 and 1. So then it would still result in the same thing. All right, cool. So one more example that I wanted to show you, which is the extension of Qt-opt, but applied to multiple tasks. So again, we use a bunch of robots to collect data for a whole bunch of different manipulation tasks. And now we collect an episode, we label it using a success detector as success or failure, and then we call this process impersonation, but it's the same as Hindsight labeling. We can use that episode, we'll see it again in a second. We can use this episode as successes or failures for other tasks and replicate it and use it for those other tasks. And then we sample from all of those tasks, and we do the Qt-opt training just on multiple tasks to do this. Now we can train a set of manipulation tasks that are relatively simple manipulation tasks, such as picking, stacking, picking specific objects, pushing, all kinds of different things. And first thing we see is that we get 80% average improvement over baselines across all the tasks. And in particular, we get 4x improvement over a single task. So if we take the exact same data set and try to train a single task, training multiple tasks seems to be much, much better. So it looks like the algorithm is able to kind of take advantage of the structure that it discovered among these different tasks. In addition to this, we see very large improvements for tasks with very little data. So the less data there is, the more kind of the structure that you discover from learning all of them at the same time seems to help. And then lastly, we can also use a pre-trained network that we pre-train on a bunch of different tasks and fine-tune it to a new task relatively quickly. So we can collect data for this new task in just one day and achieve 92% success for that task that we've never seen before. But we use this neural network that we trained here as a pre-training, and this is the task that we tried it on, which is this covering a block with a towel. All right, so we talked a little bit about data sharing and multitask Q-learning. Are there any questions at this point?
There was a question in chat that said, in the previous case, shouldn't every episode of the drawer benefit one of the tasks? Because the doors open, the doors close.
Right, so it would benefit it in the Q-learning case. So just to repeat the question, in the drawer case, wouldn't any episode actually benefit either the drawer opening or drawer closing? It would benefit it as long as you use something like Q-learning. If the rewards for the task that you're relabeling it to are 0, then they don't contribute to the policy gradient case. Yes?
Is that Same example, so for Q-learning, you could use the door opening data to train door closing, but if you only have the door opening data, that still won't be enough though, right?
Right.
You could only use it to augment.
Right, yeah, that's a great point. So yeah, the question was in the Q-learning case, if you only had data from one of the tasks, like closing the drawer, and you've never seen opening the drawer succeed, you don't have that in your data set, Q-learning still wouldn't help you because you wouldn't be able to discover that. So you can use it to augment the data, but not necessarily to kind of generate the data fully. It shouldn't hurt. Yeah, I think it shouldn't hurt. I think that's right. And probably when the drawer is completely closed and you only have the opening data, you're only trying to open it, then the reward function for the very initial state would be high, and therefore this is an example of drawer being open and would probably still work. All right, so there's one last point that I wanted to get to, which is actually the most important. So this is the goal condition reinforcement learning. So we talked about this goal condition RL and how we use the states as the description of a task. And this is actually the topic of homework 3. So how would it work with hindsight relabeling? So again, we have our data that we stored. We stored the states, actions, and now the task description is the actually goal state that we want to get to, SG. So we do it using some policy. We store the data in the replay buffer, and now we can perform hindsight relabeling. So now we can relabel the experience that we just collected, but we can relabel it using the last state that we achieved as the goal that we wanted to get to, right? So now any state in the trajectory is a potential task description. So what we can say is that you perform some kind of trajectory, random trajectory, but you can always say that the last state in the trajectory is a goal that you wanted to achieve, and now you have a successful example of you trying to achieve that goal, right? So we can do this. So now we take the last state that we achieved, and we use that as our SG, right? This is our task that we wanted to, where the reward is the distance between the current state and the final state that we got. So it's kind of like, every time we're doing something, we're pretending that this is what we wanted to do. All right, then we store that experience in the replay buffer and update the policy using the buffer, and we iterate over this. Now, can you think of any other relabeling strategies? Actually, we're running out of time, so let me just tell you. In terms of other relabeling strategies, we can also use any other state in the trajectory, right? We don't have to only look at the final state. We can look at any of the states that we've encountered and just say that this was the goal, and now this sub-trajectory is the trajectory that I wanted to get to. The result of this is that it helps with exploration. And this was actually shown in this original hindsight experience replay paper at Europe's in 2017, where we have goal condition RL, a simulated robot manipulation domain, where we were trying these 3 different tasks, pushing, sliding, and pick and place. And we can see that when we apply here, so this hindsight relabeling with goal states, it actually works much better, and it can get to higher rewards, or it can get there much faster. All right, I'm going to skip the image observations, but I wanted to tell you one more thing. So we can actually use that insight for better learning and do kind of reinforcement learning without doing reinforcement learning at all. And to actually learn a little bit more about this, I encourage you to take a look at this blog post or this paper right here. So if any data is optimal, because we can always relabel it, then can we just use supervised imitation learning instead? And the truth is that you can. So you can collect data using any policy. Then you can perform hindsight labeling. So in that case, you'll take that experience and just pretend that the goal that you ended up in was the goal that you wanted to achieve in the first place. And then store the relabeled data and update the policy now using the supervised imitation. So you're just doing imitation learning, right? So we have the behavior cloning case, and we'll be just conditioning on the goal state. And now, since any trajectory can be relabeled as an example of a successful trajectory trying to get to that goal that you actually got to, we can now do supervised imitation learning on goal condition imitation learning on any data set. And there is one example right here where this is the work by Corey Lynch et al. Called Learning Latent Plans for Play, where they collect some kind of data where they ask humans to just play with the environment. So they just record it using some kind of teleoperation tool. They put some VR headsets on people and ask them to just do anything that you find interesting in the environment. So they have the robot play with the environment a little bit. And now they can use this unstructured data, relabel it using our goal condition imitation learning, and now they can set any goal, right? So this is, for instance, a goal image that they are trying to get to, and then the robot is trying to do everything possible to get to that goal. So it tries to open the cabinet, press the right button, and so on to get to the goal. So you can collect this kind of unstructured demonstration data set without any tasks, anything in mind, then relabel everything in hindsight afterwards, and then have this goal condition policy work quite well. All right, so we talked a little bit about all four of these things: the Q-learning, multitask imitation, policy gradients, multitask Q-learning, goal condition RL. There's a lot of remaining questions that we'll answer in the next few weeks. Can we use a model? What about meta-RL? What about exploration strategies? And what if we can't collect any new data? What about hierarchies of tasks as well? So we'll be talking about it in the next set of classes. Few additional RL resources if you're interested. These are really useful. Thanks a lot for coming, and if there are any questions, I'm happy to take them now. Thanks.